Okay, so hello and welcome to part 3 of the silo problem series for E4010. This is being recorded almost a year after I recorded and published the first two parts of this problem. The reason I'm creating a third part here is basically because I realized towards the end of the second video I just sort of say, look, you can use Desmos, and this is what I did in Desmos, when actually Desmos can be a little bit unintuitive for some, or maybe there's some skills that maybe I should have showed to demonstrate to students how you can create a graph in Desmos. So this part of the problem here I really should have touched on a little bit more. Just to very quickly recap, and I mean very quickly, I've produced some slides here. So this is kind of what we did in the first problem here, and we landed on these values of 5.35 for height, 1.78 for width, and 2.49 for cross-sectional area here. In the second video, we did something that looks like this, where we determined the area of the orifice through which the liquid storage silo is being drained. And I've presented it maybe a little bit messily here, but we've kind of got this idea of a general form, and we've got this idea of a particular form. Okay, so what do I mean by a particular form? Well, by a particular form, I mean a equation that is describing the relation here that is specific to our liquid storage silo. When I'm talking about a general form, I'm talking about, well, this is the relation between the fluid contained in the liquid storage silo and time as it's being drained, but for any cylindrical liquid storage silo you like, where you can just insert your values here for the orifice, the area of the orifice through which it's draining, and the cross-sectional area as well, and also C, which I'll get to here. So I've kind of taken those slides that I've gone through there and picked out some key ideas. First of all, these values for HWAC and AO, and I've also introduced this idea of U, where if you recall from the problem, I say the storage silo has 10% ullage. This is what capital U is representing here, 0.1 for 10% ullage. Okay. And I've also picked out this idea here. This is how we calculated our value for C. So we found this equation here from deriving a formula from converting kinetic gravitational potential energy into kinetic energy, and we had a differential equation. We integrated it. We landed on this. We then substituted it in an initial condition. So we said when t is equal to 0, v is equal to 12. Therefore, when I let v equal 12 here, and t equals 0 here, I can find that c is equal to 4 root 3. And then taking this general form, I can substitute in 4 root 3, and then I land on this particular form. How might I, for starters, how might I demonstrate this particular form in Desmos? So this really is a tutorial for Desmos here, and I can just kind of replicate this particular form very easily. I can literally write in v equals open brackets minus 0.01155t plus 2. If you want a shortcut for the square root here, just type in sqrt and there it appears. And you can put the root 3 in there, close brackets, and all of that squared. If I want to do a shortcut for that, I'd do Shift 6. At least it's Shift 6 on my keyboard for the little hat symbol, and put a 2 in there. And here I have my particular form here, and I can tell it's my particular form. Right now, it feels like the horizontal axis is a bit too long, in a sense. I could just zoom out, but now I've kind of lost my y-axis, right? So one way to get around this is if I hold down Shift on my keyboard and scroll, I can kind of hone in on one of the axes here, right? So if I don't hold shift and zoom in and out and scroll up and down, I can zoom in and out. If I hold shift, I can kind of concentrate on one of those axes. So let's make this a little bit more visible here. Lovely. Right. So you can see we've got this initial condition here where t is equal to 0 and v is equal to 12. And we've got this end condition here where t is equal to 300 seconds or 5 minutes. And the volume in the tank is equal to 0. So this is what we expected, right? This is what we expected to see. Thing is, though, what if I sent you a follow-up email and said, you know, I don't want it to have 10% LOG anymore. I want it to have 15%. Or, you know, I have these new specifications for a different liquid storage silo. You might be thinking, oh, you know, I've created the graph for this specific silo, but I haven't created the graph for kind of the general form of a cylindrical kind of liquid storage silo. How might you do that? Well, we can make use of this idea of the general form here. And you might be thinking, Bertie, I can't create that because there's loads of unknowns in it, right? There's A0 here, AC, I know G, it's 9.8. There's C here, it's too many unknowns. Well, let's find out. So I'm going to type out this equation here. I can say V. I'm not going to use the subscript. Oh, you know, screw it. I'm going to use the subscript. If you want to use subscript in Desmos, it's underscore fluid, and I can go equals, and let's type this in. So I can say minus A underscore O, capital O, over 2 forward slash to do a fraction here. Again, I can use this square root idea. 2G over A underscore C T. I want to be outside of the square root there. Oops. Plus C over 2. And notice all of a sudden I've got all these add slider things. The ones I want to define here really are A0, the area of the orifice here, AC, G, and C, I suppose. And notice now we have this, let's just make this full screen here. We have this blue line here that's representing our general form, except it's looking not great at the moment. It's not looking correct at all. Why? Well, because all of our unknowns have taken a value of 1. Let's define them then. So G, we should know, takes a value of 9.81. I don't really want to change its value. I don't want to see what happens when I change its value, so I'm just going to type in 9.81 for both there. C, we understand takes a value of 4 root 3. I'll get back to C in a minute, but let's just type in 4 root 3 here. AC, let's have a look here. AC takes a value of 2.49. 2.49. And AO takes a value of 0.00824. And notice there are some sliders here, so I can change the value. And when I change the value of the constant, it will change the value of, or it will change the appearance of our blue equation here. But let's ignore that for now. I got a little carried away there. Okay. One thing I wanted to touch on. This equation isn't quite right here. I should have put in squared there. Okay. So clearly the blue graph is overlapping with the red graph here. So the general form is taking the same values as the particular form. When I change one of these constants, it affects the graph. You can see that clearly. You might think to yourself, okay, this is all correct. It's not quite correct just yet. The reason why is because take note of the fact here that C, when we found C, it is kind of a function of the initial fluid in the cylinder. We said, you know, in order to determine C, we're going to sub in our initial condition here, so we understand that when T is equal to 0, the volume of the fluid is 12, so we can substitute those values in and solve for C. But what if the initial value of the fluid wasn't 12? How could we generalize this? You could introduce, I suppose, this idea that I made earlier. So if 12 represents the initial fluid, we could represent that algebraically like this. And then I guess we could substitute that into this general form here. But no, this is kind of self-referential. This isn't going to work, right? I'm saying that, you know, V fluid is equal to blah, 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 and inside the equation here it's saying the initial value of V. It's self-referential. It won't work. So we need to find another way to express this, right? We need to find a way to express this differently so that it can kind of work. Let's just snatch this idea out of our equation again. See if I can highlight it here. Let's just put it here. So we want another way to describe the initial fluid in the tank. One way we could describe that is we could describe it as the cross-sectional area of the tank multiplied by the head, where the head isn't necessarily the whole height of the tank. The head describes the height of the fluid inside the tank, okay? And we understand that this tank has 10% ullage, which would mean then that the height of the fluid in the tank, at least initially, is 0.9 times the volume of the tank. So we could say here, we could describe this alternatively. Let's insert an equation here. We could describe this alternatively as 2 times AC times 1 minus U, where 1 minus U is that 0.9 idea, times H, where H is the height of the cylinder here. Okay. All to the power of a half. Oops. All to the power of a half. Okay. So we want to kind of take that idea and where'd it go? And put it into Desmos here. So instead of just writing 4 root 3 in here, I'm going to write in 2 AC times 1 minus U H all to the power of a half. So let's just put all these in brackets and put this to the power of a half. Okay, and we need a value for U here, and we need a value for H. So we understand that H is 5.35 here. And we understand U is 0.1. And we can see that, again, the general graph, or the blue graph here, is overlapping with our particular form. So we know that we've done this correctly now. Okay, so let's take a look at this then. If I want to kind of hide one of these graphs, so let's say I wanted to hide the red graph here, the particular graph, I can just click on this here and it's gone. and all I see here is the blue now. I can, like I was saying earlier, if I were to send you another email asking, now I want to know what the dimensions of the liquid storage silo are when I've got this specification or this specification, all of a sudden now we have a more general form here, right? We can play around with the height of the cylinder. It's clear that when we increase the height of the cylinder, it takes longer for the cylinder to drain, which makes sense. I can play with the ullage here, although the ullage really should go from, let's say, 0 to 0.5 or something like that. I can play around with the ullage here. I can play around with the cross-sectional area. I can play around with the area of the orifice. That really should go from something very small to something small but not so small, something like that. Oh, let's make that a bit bigger. Let's make it even bigger. Okay. You know, we can play around with this now. We have a general form for our graph. So I understand that what I've shown you guys here is quite advanced, and I suppose some of these techniques in Desmos, are quite advanced mathematical skills, but they are very useful when you're wanting to kind of visualize things graphically in this way. So don't be scared of Desmos, and feel free to have a play around with it. My last point would be, in your email, I'd suggest producing something a little bit like this, right? Where I've taken a screenshot. I've taken a screenshot of the graph here. I've shown where the starting condition is. I've shown where the end condition is. I've shown a particular form for the graph, and I've also shown a general form for the graph here. So if you have any questions or comments about that problem, please feel free to leave them down in the comment section down below. I'm sincerely hoping that some of you guys will have useful questions and comments here. Otherwise, thank you very much for watching.